Today we're going to review some factoring. So the main factoring we're going to talk about today is GCF, difference of squares, and grouping. We'll talk about trinomials tomorrow. So when we're factoring, the most important thing is to always check for a GCF first. So essentially this is going to be our step number one, because we always want to pull out a GCF first if possible. After that, then it kind of depends on the number of terms. So if it's 4 terms, we look to do grouping. If it's 2 terms, we look to do difference of squares. Then we're going to go into a little bit more details about this, but I feel like this flow chart is really nice. So if you like it, I would recommend printing it off because it kind of helps organize your thoughts when you are doing factoring. So let's kind of continue on to the notes. So first we're going to talk about greatest common factor. The greatest common factor is the greatest or the biggest number that is a factor, or sometimes we'll call it a divisor, of both the original numbers. So for example, if I said what's the GCF of 20 and 48, well, I shouldn't put a plus sign there. Well, 2 would be a factor of 20 and 48, but it's not the greatest common factor. The greatest common factor of 20 and 48 would be 4. So when we're thinking about greatest common factor, we're thinking about the biggest number that divides both. So if I'm looking at this first example, I have 36 and 54. So I'm thinking about common factors. So the first common factor I think about is 6. So let's say I divide each of these by 6. If I divide by something that I think is the greatest common factor, and there's still a common factor between the end answer, meaning like these both are still divisible by 3, that means I didn't pull out the greatest common factor. So if you're ever having trouble thinking of the greatest common factor, one trick that I use is I will make a little T-chart for each number. So if I have 36, I know factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. Factors of 54 would be 1 and 54, 2 and 27, 3 and 18, I don't think 4 works, 5, 6, and 9, and that's it. So once I think about it and I make those little factor trees, I can compare and I can see, oh, the biggest number that they both share is this 18. So that's actually going to be my GCF. So my GCF is going to be 18 for both of them. Now if I look at the variables, my first one has 2 x's, my second one has 1 x. So the GCF between both of those is just 1 x. So then I want to look at the y's. I have 1 y in the first and I have 2 y's in the second. So again, my GCF is just going to be 1 y, because it's going to be the most that I could take from both. I can't take 2 from both because one of them only has 1 y. Then my second term has a z, but there's no z in the first term, so that can't be part of the GCF since I can't take it from both terms. So my GCF for this first one is just going to be 18xy. All right, let's put this into action. So I'm going to look at the one right below this 12a squared plus 16a. So we're using the reverse distributive property. So essentially I'm looking to take out the greatest common factor. So if I look at 12 and 16, I need to think about what's the GCF. So 12 and 16 are both divisible by 2, but I don't think that's going to be the GCF. So if I need help again, I can make a little chart. So 1 and 12, 2 and 6, 3 and 4, 1 and 16, 2 and 8, 3 doesn't work, so 4 and 4. So once I make my little chart, I can see that my GCF for both of these is 4. So that's going to be my numerical GCF. So I'm going to divide each of these by 4, and my 4 is going to go out in front of the parentheses. Now if I'm looking at my variables, I have a squared and I have a. Well, I can take one a from each of them, so that's my GCF as a 4a. Now, when we're factoring and we're taking out a GCF, we're essentially dividing out that GCF. So I put the GCF of that 4a in front, and then in my parentheses, I'm going to put the remainder after I divide. So 12a squared divided by 4a is going to be 3a. 16a squared divided by 4a is going to be 4. And so this is what my final form will look like after I factor by GCF. I can do a similar idea in the next problem, except for I just have 3 terms, so I just have to be careful that I think of the GCF for all 3 terms. So if I'm looking at 18, 12, and 9, well, 9 does not go into 12 or 8, does not go into 12. It does go into 18, so 9 can't be the GCF, so then another factor of 9 would be 3. So 3 is going to be my GCF in terms of my numerical GCF. Then I'm going to have to look at my variables. So I have 1 C here, 2 C's here, and 1 C here. So I can take 1 C out of each one. Then I have 2 D's here, 1 D here, and 1 D here. So again, the most I can take out is just 1 D. All right, so now that I figured out the GCF, I'm going to divide each term by the GCF, and then I'm going to write the remainder in my parentheses. So 18 divided by 3 is 6. C divided by C will divide, so there's no more C's. And then D squared divided by D is D. Then I have 12 divided by 3 is 4. C squared divided by C is C. And then again, D divided by D divides, so there's no more D's left in that middle term. And then I have 9 divided by 3 is 3, and then C divided by C and D divided by D both divide. So this is what my final answer will look like for this one. So GCF is extremely important because it's always going to be the first thing you check for when we go into factoring. It also leads well into factoring by grouping, because when we factor by grouping is when we have 4 terms. And we're essentially going to group them into pairs and then take the GCF from each pair. So when we're factoring by grouping, we are taking pairs of terms and grouping them together. In order to factor. So anytime we have 4 terms, we're going to do something called factoring by grouping. So if I look at this first example, I'm going to group this into pairs. So I'm going to take my first 2 and my second 2, and I'm going to put parentheses around them so that way I group them into pairs. Then from each pair, I'm going to take out the GCF from each pair. So if I look at my first pair, I have 4AB and I have 8B. So my GCF for 4 and 8 is 4. And then for A, B, and B, the GCF is B. So I'm going to be taking a 4B out of each of these. When I take a 4B out of each of those, I'm going to write the remainder left on the inside, just like we did above. So I'm going to have A plus 2 left on the inside. Then I'm going to do the same thing for the second pair. So the GCF of 3 and 6 is 3. So I'm going to divide each of these by 3. 3 goes on the outside. And then when I divide it out, I'm going to have A plus 2. I did not take a variable out of that one because there was only an A in the first term and there was no variables in the second term. Now, to write my final answer, when I get to this step, I know I did it right because I have this A plus 2 is the same. If what's in your parentheses is not the same, then you made a mistake, so you need to go back and check your work. So when I'm writing my final answer, I'm going to take what's in the parentheses and I'm going to write it just one time. Then I take the front numbers, so in this case the 4A or 4B, excuse me, and the 3, and those are going to go in the second parentheses. I'm going to put a plus between them because this 3 was a positive 3. If it was a negative 3, I would have put a minus between them. So again, you're going to take that part that's the same, you're going to write that just one time, and then you're going to take the 2 front parts and put that together in a parenthesis. All right, let's try this for the next problem. So I am going to first group this into pairs, and then I'm going to take the GCF from each pair. So if I look at the first one, I have 2 and 7. Well, 2 and 7 don't have a GCF other than 1, so that means my GCF must be a variable. So if I look at both terms, I can see they both have an x. So that means my GCF must be the x. So I'm going to take an x out of each one, and my remainder will be 2y plus 7. Now, my second pair, I have negative 2y minus 7. They don't have any variables in common, but I notice they're both negative. So I'm going to take out a negative 1. And this will lead me to get 2y plus 7, which is good because I want what's in my parentheses for both to be the same. If I only took out a GCF of a positive 1, then my parentheses wouldn't match. So to write my final answer, I'm going to put 2y plus 7. So I'm going to write the one that's the same just one time. Then I'm going to take this x and this minus 1, and that's going to go in its own parenthesis. And this will be my final answer. Let's do one more just to make sure we're on the right track. So I'm going to skip down to this second to last problem right here. So first I'm going to start by grouping, and then I'm going to take the GCF out of the first pair. So if I have 12 and 21, my numerical GCF is a 3. And I notice they both have an a in common, so 3a is going to be my GCF. So when I divide by 3a, my remainder is going to be 4c plus 7d. Looking at my second pair, I have 8 and 14. So my numerical GCF is going to be a 2. And I notice they both have a b in common, so 2b is my GCF. And my remainder, my parentheses, will be 4c plus 7d. Again, what's in my parentheses should match, and it does. So I'm going to write the one that matches just one time. And then I'm going to take my 3a and my 2b, and I'm going to write 3a plus 2b. Our last type of factoring for today is called the difference of two squares. So a difference of two squares is when you have two terms that are both perfect squares and are separated by a subtraction sign. So what does this look like? So an example of a difference of squares would be x squared minus 4. X squared is a perfect square, 4 is a perfect square. So any variable with an even exponent is a perfect square because it can be divided evenly into two parts. So 6 is not a perfect square, so that's not a difference of squares, that's not a difference of squares. This is because 9, y squared, and 16 are all perfect squares. Not. This one is, it's a little bit tricky though, because if I rewrite it like this, then it's a difference of squares. And since these are equivalent, that is technically a difference of squares. That one's a little tricky though. This is also a difference of squares, because 9 is a perfect square and so is 1, and m to the 6th power, well that's the same as m to the 3rd times m to the 3rd. So it is a perfect square. This is also a difference of squares. This is not. This is not because it's addition. This is. 1 is a perfect square. That's probably one of the most forgotten ones. 81 and 49, both perfect squares. 25 and 100, perfect squares. 481, perfect squares. This is perfect squares, but this is not a difference because it's addition. So those are some examples of a difference of squares. So now, identifying them is the first part of the battle. The second part of the battle is now knowing how to factor them. So when I have a difference of squares, I always break them down into the two parts. So for example, x squared is x times x, 25 is 5 times 5. And a difference of squares will always be written in two parentheses, One of them will be plus, one of them will be minus, so I have x and x, and then I'm going to have 5 and 5. So you're always going to take the first one and how you broke it down and put it in the first spot, and the second one and how you broke it down in the second spot. Let's do a couple more examples. So number 2, x squared is x times x, 36 is 6 times 6. So I would have 2 sets of parentheses, and I would have x and x, 6 and 6, 1's plus, 1's minus. You're going to have a similar situation in number 3. So x to the 4th is x squared times x squared, and 16 is 4 times 4. So I'm going to have x squared, 4, 4, 1's plus, 1's minus. Now this is a little bit of a unique problem because actually you get a double difference of squares. Because once I factored it, this is still a difference of squares. So that's going to have to factor again. And that'll factor into x plus 2x minus 2. But then I still need to bring down this first part. And then this would be my final answer. So once in a while we'll have those interesting ones where once we factor it, it can actually be factored again. You'll see more of this in advanced algebra, but it'll happen once in a while in intermediate algebra. So number 4, this looks like a difference of squares, but the key word is that it's not a difference because of that addition sign. So this is actually not factorable because there's no GCF other than 1, and it's not a difference of squares. If we look at number 6, again, I want to break this down. So I have 4x squared. So how does that break down? Well, 4 breaks down into 2 and 2, and x breaks down to x and x. So 2x times 2x would give me 4x squared. 49 is 7 times 7. So now when I go to write this in the factored form, I'm going to have 2x and 2x, 7 and 7, and then I'll have a plus and a minus. Let's do just one more of this type before we go on to the next. So 25x squared. Well, that's 5x times 5x. 16y squared is 4y times 4y. So when I go to write this in the factored form, 5x, 5x, 4y, 4y, 1 is plus, 1 is minus. Now, sometimes the difference of squares is going to be camouflaged by a GCF. That's why we talked about at the beginning, it's so important to always check for a GCF first. So if I look at number 9, my GCF is 2. So I'm going to divide a 2 out. So I'm going to get 2 times x squared minus 9. Once I divide out that 2, I can see that x squared minus 9 is a difference of squares. So this will actually factor again into x plus 3, x minus 3, but this 2 is going to hang out in front because I factored that out first. So sometimes we're going to have to do a GCF and then do another step. So keep that in mind, always check for that GCF first. If I look at number 10, similar idea, I see I have a GCF of 3. So I'd have 3 times x squared minus 25. Well, x squared minus 25 is a difference of squares, and it factors into x plus 5, x minus 5. And so then this would be my final answer. The GCF won't always be that first number, so like at number 12, if I look at 54 and 6, the GCF of those would be a 6. And I'd be left with 9x squared minus y squared, which is another difference of squares. 9x squared is 3x and 3x. Y squared is y and y. 1 would be a plus, 1 would be a minus. So keep in mind, difference of squares can sometimes be hidden by a GCF. If you have other questions on factoring, please let me know. Otherwise, you can move on to the practice.